Hey, I'm Nevin Lieber. I work at Argonne National Labs. I work on SYCL, on COCOS, and I'm part of the SYCL standardization effort and part of the C++ standardization effort on C++. I can never remember my titles, but and Michael Wong still has far more titles than anybody. But I'm vice chair of the Library Evolution Working Group Incubator, and also on this vice chair of the US C++ Committee and the admin chair. And so SYCL doesn't have complex number support, and for high performance computing, we need it. So first did a survey of what's out there. All right, C's got like an extra keyword, underscore complex, that you can make, which basically creates a struct of two values. C++ has a template, standard complex T. Right, CUDA has CU complex, and then thrust complex T. OpenMP kind of relies on whatever's underlying, it doesn't care. And we're on COCOS, we have our own complex number as well. And because we're historically based on OpenCL, right? There's no real support for complex numbers. And there's kind of been some fragmentation in the ecosystem, right? For Intel gave us an extension for doing using standard complex. So why don't we standardize that, right? That's the first question. Well, implementations, they're not actually at the point of 17 and 20, they were not guaranteed to be trivially copyable. There was nothing that said that. It kind of implied it, but it never really said that in the standard. In practice, they all are, right? We need trivially copyability because we memcopy things between the host and the device. And SYCL itself doesn't really guarantee things have the same representation, endianness, right? Padding between host and device. I believe it should, while it says we like to address that, I would like to address that in SYCL next. I don't think you can be sound and not, you can't change padding, because if you memcopy it, I can ask the size of at compile time and what it has to return the same number, both on the host and on the device. And it's at compile times, so it's not really a host call or a device call. So that would be what's called an ODR violation, the one definition rule. And if you violate that, it's undefined behavior, all bets are off. And plus the implementations are not guaranteed to have, not have host only features. They could have, exceptions in the middle or virtual functions. Right. And we on the SYCL committee, we wrestle with this a lot. We would like to use a lot of stuff in the standard library, but we can't guarantee the implementations don't do things like this. Now, implementers are not trying to make our lives hard, right? They really want to create something that's better, that people will use. But as far as specification goes, we don't actually specify that, because we only specify interfaces, not implementations. I mean, in practice, there's no reason to use a virtual function in a complex number class, or a regular C++ exception, right? There were, some systems like Microsoft might have floating point exceptions and try to map them into C++ exceptions, but that's not a good idea either. And there's no guarantee that standard complex of SYCL half would work, right? There's kind of the standard complex template, and then there are three specializations, and those specializations are needed because there's some implicit conversions and some explicit conversions, depending on if you're losing information. Like if you're going from a double to a standard complex double to a standard complex float, you want that explicit because you will lose information, and you want to make sure that you as the programmer are saying, yeah, I'm okay losing information here. You just don't want to implicitly lose information. And so it's really not future-proof. Well, why not 23, right? Because there were a few little changes in 23. It is now guaranteed to be a trivially copyable type. It's right, it takes T, must be a trivially copyable type. Must be what's called a literal type, and roughly that means can be used in constexpr. And must be a numeric type, and that means it has to be default constructible, copyable, destroyable. And none of its operations can throw exceptions. It still doesn't quite say that TS, what happens is not a floating point type. And if all that's true, by the way, standard complex is also a trivially copyable literal numeric type. But again, as I said, it's just, no operations throw exceptions is about the interface, not about the implementation. The implementation still could theoretically internally have a try-catch block. Again, in practice, not likely. And if you get some more guarantees with constexpr, because you can have a try-catch block, but you can't throw an exception that would actually be caught in there. And it's only guaranteed to work on C++ 23 floating point types, or what they've also added some extended floating point types. Like there's float 16, float 32. I can't remember the exact names of them, which are optional. And we've kind of recently debated, should SYCL half be a C++ extended floating point type or not? And we've come to the conclusion, no. And one of the reasons is 23 has a requirement that if you have a floating point type that's supported, you have to have functions for absolute value, floor, all the trig functions, and they have to be in these headers. And we don't really own those headers. Those are system headers. You know, this would probably require some front-end work to make sure we get to our headers instead of the standard ones. We don't want to require that. And it's kind of unclear. Like we kind of sometimes play a little fast and loose with the rules, like what has to be supported, because you know, it really does say complex of long double has to be supported in C++. That's one of the things. We can say that's not supported on a device, but it's not clear that we can say that and still say we're supporting C++. And another thing, as part of standardization, we don't quite have clear is there's really three things, right? Is it supported on the host? Is it on the device? And is it at compile time? And that's kind of a different thing than either the host or the device. And like on the device, we don't want to require emulation. A lot of people, it would go slow. A lot of people aren't going to want it. It's a lot of work for implementers. And if we're making implementers do work, they should have customers that want the feature. And a compile time, right, there is actually something in the standard. If you want to use what's called a user-defined literal, like I want to say 3.14_z to make a complex literal, this parameter is required to be a long double. It can't just be a double. It can't just be a float. I was there when we first voted this in. I didn't know nothing about HPC. We go, yeah, of course, long double is the largest possible floating point value. Of course, that's what we want. It's a compile time. You want to take every possible value you can. Well, because of that decision, yeah, we'd like to be able to support this. So we came up with a proposal for standard complex, for SYCL complex. And as part of this, we have a reference implementation and a way to do some validation of that implementation. Kind of started in February of 2022. CodePlay started getting involved around May. And then LLVM, January of this year. It's still a proposal. It's really close to being put in, but we still have little things to work out about the exact specification of it. A few things I found while doing this presentation, actually. So what are the differences between the two? Well, we know we can use it with SYCL half. Probably the biggest one. There's no long double support right now because some platforms don't support it. We can convert to and from standard complex, but we cannot do type hunting between, say, a C array and SYCL complex, which is something I'll show you in a little bit. You can do with the C's with C++ standard complex, and it's the only type you can do that with. Our operators are hidden friends, and I'll get into that in a little bit. And we support fast math. And there could be some future extensions, like maybe we'll do it, there's a proposed extension for M array of complex numbers. Possibly do it for SYCL-VEC as well. Another thing that happens that's not on the slide is when you initialize a complex number or you default construct one, it actually initializes it to 0, 0. That could be a performance. If you know you're going to overwrite those values, that could be a performance hit. Maybe in the future we'll add a way so that you can have it uninitialized. There's issues with uninitializing it, like if you can't copy something that's uninitialized, especially if it's got like a floating point exception, because it's uninitialized, right? You don't know what the bit pattern is going to be. And in general, in C++, it's undefined behavior. So for complex numbers, we're going to support all the math functions, and then we're adding kind of obvious ones, right? The real part, the imaginary part, the square the magnitude, or want to convert from polar coordinates. So hidden friends. So you may have heard this term, and it's not a great name for things, because what's it hidden from, right? The code's obviously there. And what it is, it means it's not hidden from argument-dependent lookup. If it sees an argument, it says, oh, from that argument, I can figure out where the call is from, what namespace it's in. It is hidden from unqualified name lookup and qualified name lookup, and I'll explain what those are in a little bit. The reason you want to do this is because it avoids accidental implicit conversions, and I'll show you which one it avoids. It gives you a smaller overload set, which means it speeds up compilation. Anthony Williams has a really good article on this, on the power of hidden friends in C++. Now, standard complex, because it comes from C++ 98, doesn't use hidden friends. Nothing at the time did. And we can't change it because those implicit conversions, someone may be dependent upon. I can't say this line anymore because there was a library evolution meeting on Tuesday that I missed because I was here. And some people proposed, I think, operator plus for concatenating strings in string views. And they now said they didn't want to use hidden friends for that. I'm going to probably fight that, but we'll see. It's weird. The library evolution group said that, but like the library group would love to have hidden friends everywhere, especially the implementers, because they want faster compilation times and they don't want error-prone conversions. So the way you do a hidden friend in C++ is it has to be the first declaration of a function. It's not just operators. Any function will do. Swap is another typical one that gets used. And the declaration must contain the definition. It must be inline there. So in this example for class X, right, operator equals is a hidden friend, operator not equal is not a hidden friend. And in this example, I have now a struct Y, which is a different type, right, that has an implicit conversion to X. So of those 8, one of those lines doesn't compile because it's a hidden friend. And it's that line. You can't compare 2 Y objects to each other. Because what happens is it does argument-dependent lookup. If it has an X, it says, okay, I will look in class X to see if it has the hidden friend that I can use. Since Y is not part of class X, right? It says, oh, there's no equality operator for it. However, this one, because it's not a hidden friend, it's a regular function, says, oh, I can convert the left side to X, I can convert the right side to X, I can compare them. This surprises people because people put these conversion operators in, they're not all, they don't think these issues through, right? These are very nuanced technical C++ issues. And the other thing is qualified lookup. One of those lines does not compile also. So what happens is because I'm using double colon, I'm saying I want to look for the one in the global namespace. This function is not in the global namespace. It's only found by argument-dependent lookup. Because it's not there, this doesn't exist, so you can't call it. There's no member function. There's no, again, so it makes the overload set smaller. It makes your compilations faster. I believe you should be using hidden friends for pretty much all your operators, but we also do implicit conversions. We kind of initially said like complex T is implicitly convertible to complex U. That's not quite true. It's explicit if it's going to lose information, like double to float. Otherwise, it's implicit. And that is the reason up until, actually, I think up until C++ 20, that there are 3 specializations because there was no way to say explicit versus implicit for constructors and conversion operators otherwise. So anyway, we're going to do the same thing between single complex T to U, single complex T to standard complex U, and standard complex T to single complex U. And we can accomplish that because in 20, this you can say explicit with some Boolean expression, say whether it's an explicit constructor or conversion operator. And the standard itself for standard complex has gotten rid of the 3 specializations and now can just use a template. And if you're doing assignment, because of those conversions, it just does the right thing. Right, a standard complex double won't lose information, so I can assign it from a SYCL complex float, but the other direction doesn't work because that would lose information. Now conversions, they change types, right? It's a small cost. usually optimized away. And you can convert between, a constant reference to a standard complex to a SYCL complex, because you get a temporary and that could bind to a const reference. But if you have pointers to these things, right, that automatic conversion doesn't happen because they really are different types. So I didn't catch this during when I was like reviewing the paper, but it kind of goes on, and at one point it says like, okay, I have something that, this is a simplified example of things in the paper. These are other ways to do it if you didn't have the conversion functions. You have bar that takes a reference to a standard complex. You have baz that takes a SYCL complex. You do a reinterpret cast, and then the sentence says, this works because both types have the same in-memory layout. That is undefined behavior. So if you go into basic.lval paragraph 1, and it's gigantic, this is kind of the summary, right? Type punning, either through unions or reinterpret casts, is undefined behavior if two types are not similar. Like an int is similar to an unsigned int, but int is not similar to a float. You can also do type punning between a char, an unsigned char, or standard byte. And the reason all this is there, because compilers assume objects that are not similar to be not alias to each other. They occupy different memory. And they do, that's one of the most important optimizations they do. There is special dispensation for standard complex and C arrays. And there's a good article on it. What is the strict aliasing rule and why do we care? It's a little more C focused, but it's still really good information. So yeah, so if you dig through the C++ standard, here's the special dispensation paragraph that lets you do type punning between basically C's complex, or actually any array of 2 elements, and standard complex, right? So this is the only time it's guaranteed to work. Everything else is undefined behavior. So here's a small example, right? So on the platform like x86-64, where there are 8 bytes, right size of long is the same as long. I have a function, writes a 1 to the long, a 0 to the long, and returns what it wrote to the long. I use a reinterpret cast to do type punning. Any guesses what the output is? Standard print just prints the number. It's the C++ 20th way of doing it. Any guesses what we get? What output we get? The first one's 0. This one's easy. This output's a 0. Well, I ran it. So if you see over here what it returns, in the non-optimized case, both on client GCC is similar. I think the assembler is slightly different, but the result's the same. It refetches what it wrote to the long. When it's optimizing it, and even just at 01, it says, oh, I knew I wrote a 1 there. I'm just going to return the 1 because long and long are 2 different types. They can't be alias to each other. So if you look, right, 0, 1 and 0, 0. Right, and the example doesn't get simpler than that, right? Because you think, oh, long and long, they're the same thing, right? Not as far as the compiler is concerned. And the problem with undefined behavior is if your code works today, it may break tomorrow. So for 23, all hope is not lost. Bitcast has been added, and it requires that the size of the objects are the same, and they're both trivially copyable. Remember, you can bitcast 2 pointers, that's fine, but you still can't dereference it because, this thing is a pointer to a SYCL complex. Even if you pretend it's that, as soon as you dereference it, you're back hitting undefined behavior. And the reason you get this is memcopy and memmove are blessed basically to be C compatible to allow this. If you're not using C++ 23, you can write your own bitcast, except you can't make a const expert. That actually requires language support. And there's other things also came in 20 and 23 that address this called implicit lifetime types. So if you need to do this kind of thing, look that up. I haven't run code with that yet, so I'm trying to. There's like standard start lifetime as, which got added to 23. I want to play with it before I like put it on the slide and say this is how you should do it. Anyway, back to you'll see why that diversion was there. It's actually it's important, at least as far as I'm concerned. So we have SYCL complex. I have no idea how to pronounce that. Just like take the vowels out, I guess. It's open source, it's IEEE compliant, and it's a header-only library. And it's based on LLVMs, libc++, standard complex, which is fairly robust on CPUs. The SYCL complex version uses SYCL built-ins. Right now, we're doing most things on one API. Runs on both TPUs and GPUs. And we have a test suite, for valid mathematical outputs, error handling. We want this to be a drop-in replacement for standard complex with the caveats I gave before. And we want this API to match the one that we're proposing. Right? Part of the vision of this is we don't want to burden implementers with having to implement this. They can just use the reference implementation if they so desire. Right, so the test suite compares results to standard complex. So we have to understand complex math, right? So you get IEEE 754, you either go to this link and buy it, or you join the C++ committee and download it because it's just another ISO standard. Join the committee. And part of that, it says operations not specified by the standard, such as complex arithmetic. Okay. Mainly, signaling of floating point exceptions is implementation defined, is language defined. C++ doesn't really say much. They just kind of punt that problem to C. And so the trig functions can be multi-valued, right? I mean, the simplest one is square root of 1 can be plus or minus 1. You got to pick one. C++ does not, in the more complicated functions, does not specify which one is picked. And specifically, the CPU and the GPU can pick different values. So our test has to take that into account, right? So we just check the inverse of the function gives you X, but of course it's floating point. That's not exact. The error handling might be different. And there's a whole area of this testing called metamorphic testing that can deal with all this kind of stuff. And C++ is not required to support half precision, although they did introduce the optional float 16T. So we do some emulation. All the calculations are done in 32-bit math. And then we truncate to 16 bits. So the underlying operations have higher precision than like a true 16-bit processor will have. We need to run across, want to make sure it works on more than one implementation. So did it under Intel 1 API, tested under IWOCL. There's some workarounds, there's some namespace stuff. People think of C++ namespace as a kind of package management. It's not, it's just a language mechanism. And it really shouldn't be used for package management. And at the time, those functions were not yet supported. Did some benchmarking, basically running this with random data. For addition, subtraction, multiplication, division, we ran it at Argonne. And turned out addition, subtraction, multiplication, roughly the same numbers, same results. One API was 50% faster for single precision division, though. That's because it uses fast math, and there's lots of optimizations that allows, like the two biggies. It allows reordering, so nativity, which floating point normally does not, and it assumes all math is finite, right? Those infinities and nands are not there. And still, the compiler didn't optimize away all the checks. So now there's an if def in there just to make sure. And it was still 20% slower. And it turns out one API doesn't scale the values, and which is just a technique to reduce some of the floating point error. So we added non-scaling to this as well. Just do it by hand, otherwise do the full implementation. And we tried it in a few applications. So Gene and G tensor. I'm not a I'm a computer scientist. I'm not like a physicist, or mathematician. But the important parts of this is it was initially written in Fortran and ported to GPUs via G-tensor. And we use a lot of advanced linear algebra, LU solvers, sparse solvers, FFTs, etc. G-tensor is yet another C++ performance portable library. There seems to be a lot of those. And its complex numbers, for one API uses standard complex, and for CUDA and ROCm uses thrust complex. And like uses those libraries, and of course C complexity above, and of course does a reinterpret cast, which is undefined behavior. This stuff is kind of ubiquitous, but it can still all break in the future. So again, be careful and start looking at the better techniques for doing it. There were alignment issues. Fortran aligns complex numbers like on floating point alignment for each of the components. Typically, GPUs give you the entire type as an alignment. So we would copy one value to another for single values and asserts for the others. If the asserts fire, if they haven't yet, we'll fix that code. So these are the steps we took. Added the header, changed the GT complex type from standard complex to SYCL complex, ran the tests and benchmarks, make sure they ran, update the SYCL backend for the GT library wrappers, and run again. There are still some more namespace issues. And it's not a package mechanism. So there's now like a SYCL complex namespace that gets in there. And then pointers complex numbers. I'm running late on my talk. Well, again, it's just everywhere, and I got to take a look and figure out how to do this right. But the results, all the tests passed, and performance and build times were unaffected. So looking pretty good. We also tried it in Milk D/, which is a benchmark that simulates four-dimensional lattice gauge theory. Again, to me, they're just weird. Not that dumb. But. Sequential version has 5 nested for loops. And the parallel version uses loop level parallelism. So the baseline implementation is just a struct with 2 members. Right, there's a second implementation, SYCL complex, and the third one, SYCL complex, essentially with fast math turned on. Bunch of different work group sizes. Did 30 runs, 1 warm up, and then 100 kernel invocations. We measured it with system clock. And these are the performance results. So the ones with the infinite NAND checking are in a lot of work group sizes, just much slower. The others are roughly in the same ballpark. It's weird. Sometimes the work group size affected it. Some of them didn't. We're not quite sure why. The baseline, again, that's just the struct of 2 members, is like less than 2% better than SYCL complex. We don't know if that'll generalize to other systems. We only tried this on an A100. And that's my talk. I did it in a half hour. That was good.
Yeah, any questions for Nevin?
Thanks. So maybe more of a comment. So I'd just like to comment on those 4 built-ins that were not implemented in HipSYCL. I think support for 3 of those has already been merged, and for the 4th one, there's an open PR.
Cool.
Any more questions?
Are people just tired of the day?
I guess, have you tested this with the other main SYCL implementation?
Not yet. Not yet.
Okay.
We plan on it. But.
Okay.
So as you already have this as a library basically available for SYCL, do you still see a need to actually have this in the standard? Or
in the SYCL standard?
Yes.
Yes, because we still don't know that we can use standard complex, right? I think our ideal would be to just use standard complex.
But would you still
We still need a specification. We can't just say use this implementation, because if we have bugs, people are then dependent on the bugs in the implementation because we said this is the specification, right? We don't want the implementation to be the specification. We want to say here's how it's supposed to work. If there's a bug, you can point it out to us and we can fix it. If we just say it's the implementation, you can't say there's a bug. You don't know, right? We don't know.
Yeah, but the question is whether you need this as a specification thing. I mean, you can use it as a library only, right?
Yeah, sure. But
Like, what's the benefit of
there's,
having?
there's
it
no,
in
because there's no
specification?
guarantee, like the math functions will work, right? If it's in the specification, someone is then guaranteed they can use this thing.
So if you overload the SYCL
Right.
apps or something like that, yeah.
Right. And normally users can't overload things in namespace SYCL, right?
Okay.
It's kind of our playground. I mean, we don't want people overloading things in there because we can break them in the future. And I know, I kind of facetiously said yesterday, you know, we break things, we feel bad. We actually have big debates on whenever we're going to break something. I mean, it's not just feeling bad. We don't want to break users, right? We want to be friendly to users. And if they put things in our namespace, it's hard for us to make progress, and we don't want to stop being able to make progress. That's a good question.
With that, we'll thank you, Devin, for your talk.